think about it. Electricity is, without a doubt, the most powerful force in our modern lives. I mean, it moves at nearly the speed of light, powering our homes, our factories, the device you're watching this on right now. But here's the wild part. How do we actually control, harness, and most importantly, measure this incredibly dangerous force when we can't even see it?
Well, welcome to this explainer. Today we are stripping electrical circuits right down to their absolute first principles. We're going to demystify the science of measuring electricity, basically making the invisible mechanics totally visible, so you can fluently read and understand any basic circuit. To map this all out, we'll be covering 4 main areas today. First, the flow, electric current. Second, the push, potential difference. Third, the pushback, electrical resistance. And finally, bringing it all together. All right, let's jump right into section 1, the flow electric current, understanding exactly what moves through the wires. So, at its core, electric current is really just the flow of electrical charges through a closed circuit. It's actually highly organized. Conventionally, it flows in one very specific direction, always from the positive terminal straight to the negative terminal of a power source. To actually capture and quantify this flow, we measure it in amperes, which you'll usually see represented by a capital A. And the tools we use for this are pretty specific. A standard ammeter handles those larger, heavy-duty currents, anything above 1 amp. But for the tiny stuff, a milliammeter steps in for that precision, safely measuring delicate currents that are 1,000 times smaller. Now, you can't just plug these meters in willy-nilly. There are strict rules of engagement for measuring safely. First off, your ammeter or milliammeter absolutely must be connected in series to the circuit. That means it literally becomes part of the main path, so all those electrical charges are forced to flow right through the meter to be counted. And crucially, you've got to match the terminals. The positive red terminal and the negative black terminal have to be aligned perfectly with your power source. Moving on to section 2, the push, potential difference. What actually makes the current flow? Seriously, what forces these invisible charges to get up and move? Well, physicists love using a classic water analogy for this, and it really works. Picture a garden waterfall. The water sitting down in the pond has low potential energy. It's just static. But a pump pushes that water up, storing this massive amount of potential energy at the very top. Then gravity simply takes over, forcing the flow downward. So if we map that right onto our electrical setup, a battery acts exactly like that water pump. It's what provides the electric potential energy. Think of the positive terminal as the top of the waterfall, just loaded with high potential. And the negative terminal? That's the pond sitting at the bottom. This energy gap between those two terminals is what we call the potential difference, or as you probably know it, voltage. And yes, it's measured in volts. Just like water naturally seeks the lowest point, electric current naturally flows from a higher electric potential to a lower one. It's this specific difference, this push, that literally drives the entire system. But how do we actually measure this push without messing up the flow itself? Well, while our ammeter sits directly in series to measure the flow, a voltmeter is connected in parallel. It sits across 2 separate points to measure the difference, rather than forcing the current to pass through it. A great rule of thumb to remember, series is for the flow, and parallel is for the push. You actually see this push quantified all over your house. You've got those tiny 3-volt button cells, your standard 1.5-volt AA batteries, and of course those rectangular 9-volt batteries, the ones you might have foolishly tested on your tongue as a kid. The higher the number, the bigger the potential difference, and the harder that battery pushes the current. All right, section 3, the pushback, electrical resistance. This is how materials control the flow. Having a push and a flow is really only 2/3 of the story, because, well, materials naturally push back. If you wire up a simple circuit and start swapping out the conductor, the data speaks for itself. Using copper gives you bright illumination and a super high flow. Swap that for iron, and suddenly the bulb dims because the current drops. Use something like nichrome, and the flow is choked down to practically nothing. So this totally proves that the material itself dictates the rules. This natural obstacle to the current is called resistance, and it's measured in ohms. It's actually a beautifully inverse relationship. As the resistance of a conductor goes up, the current flowing through it comes down. Now, you might think resistance is a bad thing, but it's not a flaw at all. It's an essential engineering tool. Think about those tiny, color-coded components you see on circuit boards. Those are resistors. Engineers manufacture them with very precise ohm values and place them into circuits intentionally. Why?
to throttle the current. This makes sure that your delicate electronics don't just get completely fried by too much flow.
Which brings us to Section 4, bringing it all together, the real-world applications of measuring electricity. So we've covered the flow, the push, and the push back. But why is measuring these invisible forces so absolutely critical? Honestly, accurate measurements are the very backbone of modern safety. We measure voltage to verify that our household power grids are safe to use, and we measure current to detect dangerous defects in appliances, to monitor massive power generators, and even to diagnose microscopic issues on a circuit board. And the tools we use to capture all this data have completely transformed over the years. We used to rely heavily on classic analog moving coil ammeters, which, don't get me wrong, are incredibly reliable mechanical workhorses. But today, the modern standard is the highly sensitive digital multimeter. These devices deliver pinpoint accuracy right on a digital display, which makes complex diagnostics so much faster and way safer than ever before.
So, there you have it, the 3 foundational pillars of electricity. Amperes measure the flow, volts measure the push, and ohms measure the pushback. By mastering just these 3 metrics, humanity literally tamed an invisible force and built the entire modern world. So now that you understand the mechanics behind it all, what invisible systems will you build next? Thanks so much for watching, and keep exploring.